Okay, good morning, everyone. I hope you are doing great wherever you are and you are finding the energy to study, do your work, and work towards being a professional, which is the goal for all of us. And let's start with today's sessions. So, the we have to look at where we are right now at the we know that we have the biochemistry, organic chemistry, and the general chemistry packed together as under the umbrella term for the chemistry part of our studying session. And excuse me, we have organic chemistry and general chemistry, and then we have biochemistry that we are going to study with the biology section. So, what we have covered so far is uh, the first chapter of the organic chemistry. Now, definitely, we will come back to this, and also, I am downloading the Kaplan books for uh, mainly the organic chemistry and biochemistry and general chemistry. I will show you later, but the yielding of these uh, passages, especially the ones in organic chemistry and chemistry, they're pretty low. Uh, the main, like one of the highest deal, I think it's the highest deal topic is biology. So we need to take that into account for investing our time into this. So after learning about the functional groups and the IUPAC naming and uh, the carboxylic acid and their derivatives and aldehydes, ketones, the hydrocarbons and alcohols. So now it's time to go for the second passage and try to uh, see what uh, we have to learn about isomers. So after doing this, we will do the flashcards on this quickly, and that will probably fill in our session for the first part of the physics and chemistry. So for physics, I am relatively good in physics, and however, we don't want to get too cocky, right? And we want to make sure that we cover all the physics chapters too. But for now, my priority is to uh, get a hold of the chemistry passages. So we have structural isomers, we have stereoisomers. What are the differences between these two? Definitely, it will help to know that. And we have relative and absolute configuration. So that's also for isomers we have these three main headers. Now let me for a second bring my so I'm finally having like two screens, like a big screen that I have in front of me, and probably you are seeing that screen, which helps me better to uh, focus on. Oops. Let's see. Where are we? Okay, I just need to bring my notes. Here it is. Okay, cool. So we have these two on the side. Okay, perfect. So now we are in our let's see where we are. We have organic chemistry, right? Did we write notes for? And the whole point is improving our the whole point is improving our knowledge and be active in these fields to make sure we are not we are understanding everything, and that is the priority here. And with that we are able to so we have these here as well. So we have now some bits of progress, so we will definitely include it here. But I want to see if we have done any organic chemistry. No, I don't think we wrote notes, so it's fine. I will make one for so apparently how we want to do this is what I'm trying to say is that there is a so this is physics and chem PC, and okay, we have org chapter 1, chapter 2 right now. Okay, I will fix things on my own free time, and then for now let's do the review here. So structural isomers, by the name we can guess. So we have to have some background understanding on isomers. These are like different variations of a compound, and structural isomers have different variations of the structure, right? So the variation lies in the differences of the structure of molecules. So they share only a molecular formula, and so the molecular formula is the same. Okay, cool. So we expect some types of isomers to not have the same chemical formula, molecular formula. And structural isomers have different physical and chemical properties. So both the physical and chemical properties are different. Cool. We also then might expect to see some isomers that share, for example, physical properties but not chemical. Now, stereoisomers. They are compounds with atoms connected in the same order but differing in 3D orientation. Interesting. So that is kind of what we expected for structural isomers, but now we need to see if stereoisomers are a subtype of structural isomers, because the main factor for stereoisomers is the 3D orientation, the three-dimensional orientation. And so Stereoisomers are compounds with atoms connected in the same order but differing in 3D orientation. So let's look at examples and see what this is about. So stereoisomers have a chiral center. And this is also called chirality. So it's 4 different groups attached to a central carbon. So whenever you have a central carbon and there are 4 different groups attached to it, we know carbons make 4 bonds. That is a chiral carbon. Now we have a 2 to the n rule, which n implies the number of chiral centers. So how many chiral centers a molecule has, that will determine the number of stereoisomers. Now, apparently we have subtypes of stereoisomers. We have a conformational isomer, and we have a configurational isomer. Let's see. Conformation. So from the word conformation, we can expect that there's a difference between formation and figuration, the figure of the molecule. Let's see. So we have anti, gauche, and eclipsed. So these things apparently can rotate, right? So they differ by rotation around a single sigma bond. So we know sigma is the first, and if you have 2 bonds, it's one of them, and the other one can be a pi bond. We'll see later. And we have cyclohexane substituents. Now, if we can draw cyclohexane here, okay, forget about it here. Let's do it here. So let's try to draw a cyclohexane. We need 1 carbon. Then because we need it to be a cyclo, we expect it to be like a cycle. Now it needs to have how many carbons? 6, right? Now, how they usually draw this is what I remember from, so we have 1, 2, 3, 4, and then we have this one is 5, and then this one is 1, 2, 3, 4, 5. We need 6, right? And then this is the 6th one, and then this is, so it's like a chair, right? This is what a cyclohexane is. So if we numbered 1, 2, sorry, I'm writing really mouse pad, and 6. Horrible numbering, but still. Now, the rotation around the single bond here, this is not a cyclohexane, however, right? Because if that is 1 carbon in behind, like this one for example, and there is another carbon that's attached to it, and then it comes to this carbon, which is the 3rd carbon, and this is the 4th carbon. So this is a butane, right? And For the butane, you can see that we have conformational isomers. And NT is when these two main functional groups attached to those carbons are on the opposite side. They are anti-opposites, relatively easy to understand. Then we have gauche. Gauche in French means on the left side. So we expect it to be a bit tilted on the left. That's why this is what you see. And then we have eclipsed, where the groups on each carbon are eclipsed. They are collapsed on each other, eclipsed should give us the expectation, the understanding. Now, the cyclohexane substituents, they could be equatorial in the plane of the molecule or axial, sticking up and down from the molecule's plane. So this is what this means. This is what it's being implied here. Do we have an eraser? Must be some eraser, right? Let me select this. Oh shoot. Let me delete this, delete this, delete this, delete this. So equatorial and axial. So this is axial, this is equatorial. This is the plane of the cyclohexane, and this is axial. So this is axial, and this is equatorial. This is axial. This is equatorial. This is axial, equatorial, axial, equatorial. This axial is this way, and this one is this way. So these three go to the bottom, and these three go up for axial rotation. For axial, whatever you call it. And then you have configurational isomers. So, for example, we have enantiomers and diastereomers. It's crucially important, I think, to know the difference between these two. So let's see. As you can see, enantiomers are like mirror images of each other. If you put a mirror in between these two molecules, you will actually see what you're seeing here. So they are non-superimposable mirror images. Now, non-superimposable means that if you put this on top of this one, it will not be matching, right? And opposite stereochemistry at every chiral carbon. So at every chiral carbon, there is an opposite stereochemistry. Now, keep in mind, configurational isomers like enantiomers and diastereomers are a subtype of stereoisomers. This stereoisomer is the main title for these, the umbrella term for them. They have same chemical and physical properties. There you go. Except for rotation of plane polarized light. Again, except for rotation of plane polarized light. So when you have a plane polarized light and you rotate it, whatever this means, so we can write it down. Let's remove all of these here. what is a what polarized light? Plain polarized light? What is a plain polarized light, and why is it not, why does it, and why does it change the physical chemical stereo properties of stereo isomers? Optical activity. It is the ability of a molecule to rotate plain polarized light. So the ability to rotate plain polarized light, that is called optical activity. And we have a D or plus, which implies right, and we have I or minus, which infers left, and so the L, I think this is L, yeah, because this D is also in small caps. So I don't know why these are different. Like I know a bit of French, and I know that droite means right. So maybe this D is coming from French, because we also had gauche here, which means left. But I don't know why the L is, maybe, yeah. But we can find a way to keep these in mind. We don't want to mix it up. We have a racemic mixture, which is a 50-50 mixture of two enantiomers, not optically active, because the rotations cancel out. So a 50-50 mixture of these two enantiomers will give a racemic mixture, and it is not optically active because the rotations cancel out. So the rotations of these two will cancel out because they're in equal amounts. Then we have meso compounds. They have an internal plane of symmetry, will also be optically inactive because the two sides of the molecule cancel each other out. So diastereomers. So we know that enantiomers are mirror images, but diastereomers, they are not mirror images. Why? How? Let's see an example. This is the same as this one, but this right here is a mirror image. Now, because one side, we have two chiral carbons here, right? And does it mean that we need two chiral carbons in order to have diastereomers? I think so, because the dia comes from that too. So do we need to have two chiral carbons in order to have diastereomers? So again, diastereomers are not mirror images like enantiomers. And we have a cis-trans subtype of diastereomer, which they differ at some but not all chiral centers, different chemical and physical properties. So we had same physical and chemical properties, which was for enantiomers. except when the rotation of plane polarized light happens, whatever that means. You'll figure it out. And both diastereomers and structural isomers have different physical and chemical properties. Yeah, I think we need also examples of structural isomers. So give me some examples of structural isomers. If anyone knows the answers to these questions, it would be a cool learning process for everyone, I believe. So, including myself. So, I appreciate that. Now we have relative and absolute configuration. So, we should not mix this, I believe, with configurational isomers. Now, relative configuration gives the stereochemistry of a compound in comparison to another compound. For example, the D and L. Okay, I think okay, this DNL was for optical activity, but this DNL is in big caps. So we have absolute configuration, which gives the stereochemistry of a compound without having to compare it to other compounds, for example, S and R. Then we have the Kohn-Ingold prelog priority rules. Priority is given by looking at atoms connected to the chiral carbon or double bonded carbons. Whichever has the highest atomic number gets highest priority. Now we have the Z and E for alkenes. Z is the highest priority on same side, and E is highest priority on opposite sides. We definitely need to see examples for these. We then have R and S for stereocenters. A stereocenter's configuration is determined by putting the lowest priority group in the back and drawing a circle from group 1 to 3. I remember this, and there are videos on this which really help. I think it's the YouTube channel from Leah Forsai, and there was another girl. They did a really wonderful job on this. So definitely I'm going to watch those. Now the R stereocenter is clockwise and the S stereocenter is counterclockwise. And we have Fisher projections. So they are vertical lines that go to back of page, dashes, and horizontal lines coming out of the page, wedges. Now, how I mean, it's now second nature, I would say, but how I know that wedges are in front of us in the 3D space, and dashes are behind us is kind of by second nature. Yeah, I don't know how to give a way to memorize it, but still, if I find anything, I'll definitely share it here. We have altering Fisher projections, so switching one pair of substituents inverts the stereochemistry. Switching two pairs retains stereochemistry. And rotating entire diagram 90 degrees inverts the stereochemistry. Rotating 180 degrees retains stereochemistry. Now here we have a compound. Do they have the same molecular formula? Do they have same connectivity of atoms? Do they have interconversion requiring breaking bonds? Do they have non-superimposable mirror images? So first step is to figure out if they have same molecular formula. Second is if they have connectivity of same atoms, same connectivity of atoms. And then the breaking bonds, interconversion requires breaking of bonds or not. And we need to know what's interconversion, because my guess is that if you can convert the groups, the atoms between the two chiral carbons, and then if they are non-superimposable mirror images. So if you have the same molecular formula, they are isomers. If they don't have same molecular formula, like CH4, those things that you write, right? C2H6, or this is, for example, CH, and then CO2H you have, and then OH and CH3. So it's C3, like O2, O3, and H6, right? So that if this one has also C2O3, C3O3H6, then it's an isomer, right? And then after the isomer step, you want to see if they are constitutional isomers, like structural isomers, or stereoisomers. So are constitutional isomers the same as structural isomers? Now, for stereoisomers, the interconversion requires breaking of bonds. If no, they are conformers. So what is interconversion in stereoisomers, and what are conformers? And if yes, if the interconversion requires breaking of bonds, you know that they are configurational isomers. So if they are not mirror images, we know that they are diastereomers. Perfect. And if they are mirror images, they are enantiomers. Okay, perfect. So now let's get on the flashcards. Once I download my Kaplan books, I just want to show you and also use it myself for doing the pre-assessment tests to see how much you know of the passage, which really helps, and those are cool. So we have the cards are piling up, as you can see, so we need to definitely keep in track with them. Now I want to see if I I'm not sure if I have to add the organic chemistry chapters one by one, or just on top of this one. So for the biology, for example, I like to do it that way. I like them separate. And We also have the Master Pankow here, which is we can close it there. We can come back to it, and let me do actually a custom session on this. So we have organic chem, perfect, isomers. We have 43 cards. Keep the 43 cards in mind. $44 we put, just to be safe. We have Orchem. I think we have it. Just name it, not to confuse it with other stuff. So org 2 isomers. Apparently it went under the site source here, which is fine. So what has the same chemical formula but have a different stereochemical arrangement of their atoms? So same chemical formula but different stereochemical arrangement. I believe when we're talking about different stereochemical arrangement, these are stereoisomers. So it's in general isomers. So if you have same chemical formula but different stereochemical arrangements, these are isomers. What isomers have identical chemical formulas but different structurally? So identical chemical formulas but the structure is different. So they are not structural isomers, they are stereoisomers. Oh, so when we have different of the like whatever you put isomer after, it means that it is different in that. So a structural isomer means that they are different structurally, and it's the same as constitutional isomers. So we can get rid of this one, like it's answered. They share only a molecular formula, have different physical and chemical properties. The only thing so far that we found have the same chemical and physical properties are the enantiomers, which are non-superimposable mirror images, right? Same chemical and physical. However, still you can change it with the plane polarized light. The rotation of plane polarized light. So structural isomers, here you have them: isobutane, butane, and stuff like this. Okay, what are connected in the same order but different in 3D orientation? So this should be for stereoisomers, since we have 3D orientation. This is a cool representation of the difference between diastereomers. So diastereomers have different chiral center rotation or priority groups. That's what makes it diastereomers. So R was for the right, from like clockwise, I think, and S, let's take a look here. So we have the R, yes, clockwise, and we have S counterclockwise. Let's see the priority of the groups. So for this carbon, it's attached to a carbon. So hydrogen gets number 4. So it goes to the back, and you do the rotation from whatever side you see it's better. So you have the oxygen attached to carbon, which makes it the 1. And between these two carbons, this one is attached to the oxygen afterwards, and this one also oxygen, but this has more, this is hydrogen, and so like this would be 2 and 3 because it's attached to another carbon too, I believe. So it would be going this way, which makes it an R, and this is still R. Now let's look at the S. What makes this the S? So this is 4. We put it in the back. Now it should go this way, right? So let's figure out. This one is our priority group over this one. So that's why we go from, and this is our number 1, the oxygen, right? And then we have the priority of, so it should go this way. For us here, we went this way because this carbon had higher priority over this one. So and also for this one, we should go so we need to definitely know our stuff for the priorities. So determined by putting the lowest priority group in the back and drawing a circle from group 1 to 3. So the highest so putting that one in the back. Okay, we put this in the back. We put this in the back, and we go this way. However, we're going this way for this one. Oh, so I believe this is how you look at it. So in order to see if it has a higher priority or this carbon, so this carbon is attached to oxygen, carbon, and hydrogen. This carbon is attached to oxygen and 3 hydrogens. So because this one is attached to the carbon and oxygen, this one has higher priority. So you give this one 1, and then 2, and then 3. So it goes this way. But I don't know why it still is R, because it should go counterclockwise. Now, this implies the fact that this one has higher priority over this one. And unless the left or rightness of the hydrogen matters. Yeah. But we got the question right. So what is when four different groups are attached to a central carbon? Is a chiral center is when four different groups are attached to central carbon. This is not chiral, but this is chiral. So for n number of chiral carbons, there are 2 to the n possible stereoisomers. So for n number of, identify a number of stereoisomers of this molecule, count chiral carbons, use formula 2 to the n, and you have 16 stereoisomers. What isomers differ by rotation around a single sigma bond? So this was for the first type of stereoisomers, which was for enantiomers. The conformational isomers, right? So enantiomers was the first type for configurational. So we have conformational isomers. So for this we are talking about anti-gauche, eclipsed. We have staggered or eclipsed, as you can see there. So the two different types of staggered are anti and gauche. This is important to keep in mind. This Newman projection shows what conformation? This is anti. The carbon attachments are on opposite ends, 180 degrees apart. This is a gauche conformation. The carbon attachments are 60 degrees apart. And this is an eclipsed conformation, less favorable because it forces more interactions between the front and back attachments, creating more strain. So this is less favorable. So we believe that anti should be the most favorable. It's like the most stable, and this one, however, puts too much pressure and more strain. It forces more interaction between the front and back attachments. For this, we can do it later. What bond is a bond which is perpendicular to the axis of the ring? So the axis of the ring, I believe it should be the sigma bond. The equatorial bond is perpendicular to, so we have equatorial. Okay, so we have the axis of the ring and we have the plane. The bond lies along the equator of the chair. So we have an equatorial bond and we have axial, right? So what bond is perpendicular to the axis of the ring? Okay, I think there's a mistake here, because for perpendicular you have the same thing, but it's on like the equatorial is on the same plane. It's parallel, right? So where do we have it here? In the plane. And axial is perpendicular. So equatorial is in the plane. So what is the relationship of equatorial bond to the axis of the plane? So if should be parallel. So let's edit it. Yep. This is how you write parallel, right? It's with two L's, right? Yep. Okay. So yeah, this is for being parallel and perpendicular to the axis of the ring. You have straight up and down, which is axial. The two categories of what isomers are enantiomers and diastereomers. These are configurational isomers, and they can only change from one form to another by breaking and reforming bonds. So enantiomers and diastereomers, you have to break the bond and reform the bonds in order for them to change into the other one, right? What are stereoisomers that are non-superimposable and are mirror images? So non-superimposable mirror images, they are enantiomers. Is there a way to connect enan like anonymous and non-enan non-superimposable? That is actually nice. Same chemical and physical properties except for rotation of plane polarized light. So let's edit it here and write enantiomers mnemonic enantiomers. I'm also gonna write it down in our mnemonics here. We can search for the mnemonics here later. So mnemonic enantiomers non-superimposable. Cool. Optical activity is the ability of a molecule to rotate plane polarized light. So we have a multi-directional light source, and then we have a polarizer. This is the polarized light, and we have specific rotation, which is alpha. We have concentration, which is C, and we have length, which is small l, and then we have an observed rotation. The polarized light is rotated here, as you can see. So let's put this for good. What mixture is a racemic mixture? 50-50 mixture of two enantiomers. Keep in mind that racemic is for enantiomers, and it's not optically active because the light rotations cancel out. So you can see here that bromine can, for example, attack from this side or the other side which gives bromine for this one going from the back is with dashes, and this one going from front is with wedges. And yes, so what have an internal plane of symmetry? It would be, so internal plane of symmetry, it would be meso compounds. Okay, definitely I would not be able to get this one. Will be optically inactive because the two sides of the molecule cancel each other out. So we have meso compounds, not meso. What's the difference? You have the bromines. So this chiral center is the same, but this one is not the same since the bromine is in the front here, and here it's the back. So, and the hydrogen is the other way. So this is, I believe, like two diastereomers, right? So internal plane of symmetry. So inside this is one of the diastereomers. This has, because they're both like, for example, R and R, they have a internal plane of symmetry, but this one they don't have it. So meso compounds, they are optically inactive because it's the same two sides. I'm sorry, because the two sides cancel each other out. So we have the 1,3-dimethyl cyclohexane. So it could be in this formation, which is not meso. This is meso. Interesting. I had heard about meso compounds before, but never went. I was never brave enough to go after the information and learn this fact. So you can identify the meso compounds through R and S. There you go. And you have substituents that are arranged symmetrically, and you have stereocenters that are opposite. So meso. You have substituents that are arranged symmetrically here, and stereocenters are opposite. It's still meso, interestingly. So this H. So this is interesting stuff. So if you still have this, and so what's the difference between these two? Like they're both same, right? Substituents are arranged symmetrically. Okay, we have to get a break, but let's just finish this concept here. So as you can see, the hydrogen is in the back. So, okay, this is a good example. So the hydrogen is in the back, which is 4. You put it in the back. Perfect. Then we give priority. So this gets a 1 because it has a carbon attached to another carbon and another carbon, but this one is attached to only one more carbon and has 2 hydrogens. This one has only 1 hydrogen, so this gets 1, and then this one gets 2, and this has 3 hydrogens, so it gets 3. Amazing. So that's why we go this direction, and you have a R. Now for this one, the hydrogen goes in the back. It's 4. Perfect. Now 1 here, 2 again here, and 3. So we have this way rotation, which is an S. So still we put the hydrogen in the back, but kind of it's not like the other compounds we saw, which the hydrogen was either on the left or right, so we have to figure that out. But still here we have the hydrogens in the back, these in the front. So it's a meso compound. because it's however it's R and S, right? So the stereocenters are the chiral centers are opposite, interestingly. Now for this one also, the bromines and the hydrogen is into the page, and here it's out of the page, and this one I'm not sure why. I think they drew it incorrectly, because here, okay, actually no, because these are on different sides. I mean, this is coming out of the page, this is going into the page, but the methanes are the CH3s are so what happens if you rotate this? You bring the bromine on top here. You then have the, okay, so now they superimpose each other, and it makes it a meso. So even if it's an anti-formation, you have to keep in mind that you can still be a meso. But this one is not meso because you cannot rotate it, right? And this will make it a meso. This is interesting. This is very cool stuff. Okay, let's take a break. My stomach is super hungry, and then we'll be back in 10 or 15 minutes.